This is Unit 7, and we're going to be going into special derivatives. So derivatives of exponential functions, like 2 to the power of x, 3 to the power of x, 100 to the power of x, and so on. Derivatives of logarithms, and then also derivatives of trig. And so in lesson 7.1 and 7.2, I'm going to be going into exponential derivatives. So you're going to be like, well, what's the difference between 7.1 and 7.2? 7.2 is going to be using any base, so any number to be at the bottom, and then to the power of x. Whereas this lesson, 7.1, I actually want to talk to you and teach you about e to the power of x. Now, e is a special number. It is 2.7183 on and on and on forever. Very similar to, how like pi is 3.1415 on and on forever. So both of these guys are rational numbers. In fact, if you take your calculator out, you should be able to find e to the power of x. Now, e to the power of x is, e anyway, is Euler's number. And so Euler was a mathematician from a long time ago, and he came up with this equation, which was something used to calculate compound interest, where let's say you put a certain amount of money into a bank. That 1 represents 100% of your money. So obviously you have 100% of your money. But carrying on to the next compounding period, you would then have this 1 over h, so that is your interest. So you're going to build some sort of interest based on how often you get the interest. Do you guys remember in like grade 11 when you started learning about like financial applications and stuff like that? You were like, okay, if you get money monthly, like interest monthly, h would be 12. And then if you got like your money daily, h would be 365. And so what I'm going to do is I'm going to show you through investigating, I'm going to start upping that h value closer and closer to infinity. Okay, so I'm really going to start to increase the number and try to get as high a number as possible. So what that means is like, instead of going 12 for 12 months and 365 for interest every day, we're now talking about, well, what if I gave you interest every second? What about every nanosecond? And so on. What's going to happen to your money? All right, now my class is going to use Nspire calculators. Since I have it right now, I really hope that they're not watching yet. But we'll do this together. Okay, so I'm first going to graph 1 plus 1 divided by, 1 divided by x to the power of x. I can't type. There we go. So this is the compound interest formula graphed. And I'm going to open up a table and split screen it. So here are all my x values and my y values. Now this is based on just an example, putting in $1 into the bank. Okay, and this would be the compound interest, so the amount of money that's left afterwards. If it was compounded once, then you're going to have $2 in the bank, and so on. Now, I really want to know what happens when you compound like every nanosecond, or how about we just talk about 10 times a year? So 10 times a year, your dollar now grows to this much money. All right, let's keep going. As x gets huge, like let's say 100. So now you're getting your interest 100 times a year. It looks like your money is going to grow towards this much, even though you had originally put in only $1. And let's keep going to some huge amount. Do you see how it's starting to approach a certain number? Like all the numbers seem very, very similar, and they're only growing by a certain amount. And after a while of doing this, as you get larger and larger x values, you're going to notice that you get closer and closer to Euler's number. And that's how it was discovered that this number does continue going on forever, but it looks like for the specific equation, as h approaches infinity, you're going to get closer and closer to 2.7183. So what I'd like you to do is try to find that e to the power of x button on your calculator, and I want you to input, I'm sorry if you can't see this, e to the power of 4 and e to the power of -1 and 2 times e, and see if you actually get these numbers, because it's just e, which is this guy, to the power of 4, and see if you get this. E to the power of -1 and see if you get this, and so on. Okay, so that's just playing with the number a little bit. Now that I've told you what Euler's number is, let's see what the derivative of Euler's number to the power of x looks like. Okay, but I think I'm going to start off small first. I'm going to start off with, instead of Euler's number, why don't we use, I'm going to open up a new graph. No, I'm going to open up a new graph. There we go. Instead of 2.7183 to the power x, you know what? I think I'm going to do just 4 to the power of x. Okay, so this is what we should expect for 4 to the power of x. This is an exponential function. Obviously, it's exponentially growing. And I can actually graph the derivative too. So let's go, okay, open up another tab. And they have this button right here, which allows me to take the derivative. So I'm doing another function, doing the derivative of our 4 to the power of, what am I writing? 4 to the power of x. Taking the derivative with respect to x. And there we go. Okay, so our original function, our exponential is going to be the blue. The red is going to be the derivative function. Since I want to compare them a little bit, I think I might want to zoom in just a tad and see if I can see anything. So there are the two. And I'm looking at their y-intercepts, and I think I want to trace those. They might give me more information. Okay, so here are our two y-intercepts. Originally, the y-intercept should be 0, 1. And if you think about it, that makes sense because 4 to the power of 0 should give you 1. But the derivative has now grown higher to 1.39. It looks like the red is still like an exponential function, but what exactly happened to it? And so it just looks like the red is a vertical stretch of the blue. If I go back to my lesson, I have the blue in blue still, but my red is now in purple. Okay, so this is our new y-intercept, and you'll notice that there was a stretch, a vertical stretch by a factor of 1.39-ish. That's what I'm going to call my k-factor. So in the next video, I'm going to talk more about these random exponential graphs and what their derivatives look like, but we kind of figured it out right now. The derivative of 4 to the power of x is just whatever this k value is, in this case 1.39, times your original exponential graph. And so what happens if it's not a 4? What happens if it gets closer and closer to Euler's number? Well, I decided to go and look at all of those as well on the NSPAR calculators, and I graphed each one's derivative and I compared them. So this guy's derivative, which is this function right here, had a stretch factor of 0.693. And when I graphed this one and its derivative, the second one was stretched from the first one this much. In other words, like this function, the derivative, which I wrote over here, is the original function multiplied by that k factor. And as the original got closer and closer to e to the power of x, I noticed that the k values got closer and closer to 1. So that's very special because if your original function is e to the power of x, you're essentially saying your derivative is still e to the power of x. Like, mind blown. When have you ever seen that before? Have you ever seen a function where you take the derivative and it's itself? No. This is why e to the power of x is actually quite special. It's its own derivative. Okay, now, if it was anything else, any other number as the base, what would happen is we can use first principles. And so using first principles, I'm just going to pretend any number would be a base of a. So a to the power of x. Now, if you do first principles, you have to sub in x plus h for the x minus just the x subbed in. Okay, now I'm going to factor out something in common. It looks like both the a to the power of x is common. When I factor that out of this guy, I'm left with a to the power of h. Minus, factoring it out of this one, I'm left with a 1. I can separate the limit of both of these into two separate limits that are multiplying each other. And since this one doesn't have an h, it's still like I can't sub-zero into anything, and so I just have a to the power of x. This was our original function. But we're calculating the derivative here. This guy over here, I'm going to call my k factor. So you'll start to notice this a little bit more, like keep this in mind for my next video, that when you take the derivative of anything to the power of x, you basically have a to the power of x again, but you're multiplying some sort of a stretch factor. Okay, now in terms of e to the power of x, that stretch factor is 1, and that's why you get the exact same function. So in this video, I'm just going to be focusing on the derivative of e to the power of x. So the derivative of e to the power of x is itself, where your k, your stretch is a 1 right here. Obviously, they can make things a little bit more difficult and be like, okay, what if instead of the exponent being just x, I threw in a function? You're just going to have to use a chain rule. So you already know, based on this guy, that the derivative of this is itself. But then you got to do the chain rule. You have to take the derivative of the inner layer as well and multiply it. Okay, so I'm going to wander over to my smartboard and we're going to do some examples together. Okay, so example number 4 says, let's take the derivative of y equals 5e to the power of x, and they want you to simplify fully. Okay, so I'm going to grab my purple, because I seem to be partial to doing derivatives in purple for some reason. Y prime is going to be, and what I want to do is I want to think of this guy, 5, and the e to the power of x as if they were multiplying, like a product rule. So keep them together like a product rule when you're doing the derivative. Let's do the derivative of the 5, which is 0. Keep the second one the same. Plus, keeping the 5 the same this time and taking the derivative of the second. So we just learned that the derivative of e to the power of x is still e to the power of x. So that is the product rule right there. And now, obviously, 0 times e to the power of x is 0. And our final answer is the exact same as the original answer. Sorry, that wasn't worded quite right. The answer is the exact same as the original question. Now, this is a mistake, and I'm going to do it purposely. A lot of people think that if you're going to do this, to take the derivative, you take this guy and bring it down and get 5x e to the power of x minus 1. You don't do it like that, okay? This is different because e to the power of x you're going to treat as one thing and the derivative is itself, so don't do it this way. Another way that you can do it instead is if you have the original function, y equals 5 e to the power of x, you can then do the derivative as a constant multiplied by the derivative of the thing that actually has an x, which is e to the power of x. And if you were to do the derivative of that, that would equal to just leaving the 5 alone and then taking the derivative of just this part, which is still e to the power of x. And you'll notice that you get the same answer no matter what. Okay, now let's try example number 5. And again, I can treat this just like a product rule. Okay, so y prime is equal to derivative of the first term, keeping the second one the same, plus the derivative of the second term. Actually, you know what? Why don't we just do this one first, keep that the same, and then the derivative of this guy, which is itself. Since they told us to simplify fully, I think I might just want to put things together. And it looks like we have in this term and this one, they both have an e to the power of x. And then you have 2x left over from the first plus x squared left over from the second. I mean, you could even take out an x, can't you? Yeah, let's do that. Equals, take out an x, multiplied by the e to the power of x, and then what's left in there is the 2 plus x. So that would be simplified fully. Example number 6, and I just wrote it out a little bit bigger so that you can see it. There's only so many hours in the day that I have to do this, and so my coworker just ended up using super small font, and I don't have enough time to change everything and format stuff. So we make do with what we can. Y equals e to the power of x squared plus 2x. So notice that this is an entire function. That means we'll have to do the chain rule. Okay, so e to the power of all of this, the derivative, is going to be itself. So y prime is itself. But then we do the chain rule and we take the derivative of that function in brackets. And so 2x plus 2. That is the derivative, but let's simplify it, make it look prettier. It looks like a 2 can come out of each of these. Let's bring that to the front. E to the power of x squared plus 2x times x plus 1. And that's as far as I would go. Okay, now I did the next one for you because there was a lot to it and it looks kind of confusing. I rewrote it in the first step right here. Notice that everything in blue is just me fiddling around with the original function to make it nice so that I can take the derivative. In this step, I changed every radical into an exponent instead of 1/2. And then in this step, what I decided to do was just simplify, maybe put some of these exponents together. Okay, like this one right here, I put together like that. Now in this step, I'm going to start taking the derivative. Let me get rid of those so that I can show you how I did that. Since this is an actual number, we can use the power rule and bring it down. The reason why I didn't let you do it before is because this was an x, and then you can't do it that way. You can't take x and bring it down and subtract 1 from it. So you can only do the power rule if that is a number, which it is, because we know that e is 2.7183, on and on and on. So bringing it down and then subtracting 1 gives me this guy right here. Since this is also a number, I can also bring it down, subtract 1. Now, since this is not a number, I can't do that the same way that I did before. And so we look at it for what it is. This is e to the power of x, and so the derivative of that is just itself. But then, since this is a function in here, we take the derivative of that function and we multiply it. So again, this guy has an x in it. We can't take the derivative like we did with the power rule. And so we look at the entire thing. E to the power of this is its own derivative. Then we do the chain rule inside. The derivative is multiplied. And the last step is just cleaning it up a little bit. All right, now example number 8, all the way in this corner. I know you can't see it very well, but y equals to e to the power of x plus e to the power of x, which is ridiculous. Why would people give you questions like this? So y prime is the derivative of e to the power of all of this is still e to the power of all of that, multiplied by. Then you have to take the derivative of this guy, which is 1 plus e to the power of x. And that's it. So this question you've seen so many times before. Find the exact equation of the tangent to e to the power of x over x squared at x equals 1. So you guys already know the tangent, we need the slope. And so to find the slope, we got to take the derivative. Okay, so y prime is equal to, and why don't we do this as a quotient rule? So quotient rule is derivative of the top, which is the same, times the bottom, minus derivative of the bottom, times the top, as is, all over the bottom squared. Okay, now I wouldn't even simplify that. I would actually sub in this 1 right away. Okay, so anywhere you see an x, let's put a 1 instead. Okay, e, I'm going to write the 1 in a second because I don't like changing back and forth between the colors. I say that, but I do it all the time. Squared, squared. All right, let's get in that red one. So this is e to the power of 1, 1 to the power of 2, 2 times 1, e to the power of 1, and then 1 squared squared, which gives us, I believe, it's just e minus 2e. Is that right? Over 1. I don't have to write the over 1. E minus 2e, which is negative e. Okay, so that's your slope. All right, except they didn't ask for your slope. They asked you for the equation. So now you got to do the equation. Y equals e x plus b. All right, so now you need your point. So you're going to use this guy as your x, but you need that y. So subbing that into the original equation, what you're going to get is, and when I do this really small on the side, y with the 1 subbed in to the equation equals to, I think it's e to the power of 1 over 1 squared is just 1, right? Which is e. This is a really weird way to write it. I'm sorry. All I'm saying is that I'm subbing 1 into the x value of my function. Why am I writing it like that? I should just write f at x or something. Here, we'll go like this. There we go. Therefore, we have a point at 1 and e. So we'll put 1 there and we'll put e over here. Plus b. So it looks like b is 0. Wait, is that right? What did I do? Oh, that's silly. Haha. Ta-da. Okay, much better. So that's going to be 2e equals to b. Therefore, y equals to negative ex plus 2e is our final equation for our tangent. And now, obviously, I'm going to hit you with a word problem. Example number 10, the number of bacteria in a culture at time t hours is given by a certain function. What is the initial number of bacteria? So we've done these questions before. Initial number means I'm going to sub in 0 for my t. And I'm going to use the original formula. Okay, and I get 31,000 bacteria. Put a therefore statement. Now in the next one, it asks for how fast a number of bacteria is growing. So when they ask me how fast, it talks about some sort of a rate. And so I know that they're looking for n prime. Okay, now what I would do is I would probably change this up so that it's a number in front of the t. It makes it a little bit easier to do the derivative. Plus, I think what I would do is take the 1,000 and multiply it in, if possible. And so I did that right here in order to get these two terms. So now I have a nice long polynomial, and I can take the derivative. So the derivative of the 30,000 is just going to be 0, and then taking the derivative of the second part is right here as a chain rule. So since they wanted it at 20 hours, I'm then going to sub in 20 into my t, and I get my answer. So at 20 hours, because it's a negative, these bacteria are dying. The growth rate is decreasing. So the bacteria growth rate is actually decreasing at a rate of 17 positive. I'm going to write 17.11 bacteria per hour. Instead of adding in the negative here, I would not do that and put the word dying instead, or decreasing. Okay, so that was our first 7.1 video, and we're actually closing in on the end of this course, which is crazy. Summer's around the corner. So I will see you next time for 7.2.